Welcome to Ask and Learn.
Okay, so for this problem, the question is how many moles of gas there are given that this gas is cooled with the constant pressure, and then it asks for the same thing, assuming constant volume. Let me see if there's anything more to that. Then change in internal. Yeah. So first, just to kind of first we want to find the number of moles in the gas. So you want to use the formula that Q is NCP delta T. And then this delta T is 40 Kelvin, also 40 Celsius. But since you convert Celsius to Kelvin by adding 273, if you subtract two different values, the 273 kind of subtracts out. So the conversion is the same, and hopefully you've seen that elsewhere. And so if we do that, we have our CP, we have our delta T, and we have our Q. So you can just say that N is Q divided by CP delta T. And if you plug in the numbers I have listed on the left-hand panel, you'll get what I got, which was that there's 21.5 moles, which is kind of a lot of gas. Great. And for part B, it asks for delta U. So delta U is equal to NCV delta T. Even though it's not a constant volume process, it's always NCV delta T. And there's like an explanation in the book if you want to read it. But I mean, it's just kind of all constructed that way. So if you use this for your N, your CV here, which just comes from the a table in the book, and your delta T is 40 Kelvin, perhaps you will get what I got, which is minus 17,900 joules. I'm just going to go with 3 sig figs here. And for part C, it asks for the work done. I don't know if it asks for the work done by the gas, but let's just double check that. Yes, work done by the gas. So work done by the gas is just going to be your Q minus your delta W. From the formula, delta U is Q plus W, Q minus the work by the gas. And so if you plug in, let's see, your Q, which is your minus 2.5 10 to the 4, and then minus a negative 17,900, which would mean adding 17,900, you get minus 7,150. So that means that there was actually work done on the gas during this process as it cooled. Actually, I'm just going to take a second and try to consider if that actually makes sense. So the gas is cooling, and we know that the pressure is staying the same. And so that means that like the pressure is kind of the number of collisions and then how kind of impactful the collisions are. So the gas is cooling, the collisions are getting less impactful. But to keep it at a constant pressure, you have to increase the kinetic energy of the atoms. And so sorry, that I realized that discussion actually didn't quite make sense. So let me go back and try to do another sanity check for this. So the work done by the gas is negative, means that work done on the gas is positive. And then it actually does make sense because the work is kind of like the force of the container inward on the atoms in the container, and the work and the displacement are in the same, or excuse me, the force of the container and the displacement of the container are kind of in the same direction. So to me, it's believable that that this comes out negative. Great. So for part D, it asks what would happen if V is constant. So if V is constant, Q equals delta U. What a sorry little Q. I'll make it slightly better. Because the work is 0. And so if the work is 0, you're keeping it at a constant volume. Then your delta U is just NCV delta T, which we already calculated here, which is minus 17,900. Okay. Great. So you're keeping it at a constant volume, and then I guess you're just kind of decreasing the pressure. So you're just pulling out the kinetic energy per atom. I don't know if that makes sense, but yeah, there we go.